In today's session, we're going to be factoring special quadratics, starting with difference of squares polynomial expressions. A difference of squares polynomial expression is a binomial whose terms are both perfect squares separated by a subtraction sign. So any polynomial that is a difference of squares can be factored by applying the following formula. So I'm going to write out our general expression for a difference of squares. A squared minus b squared. Difference meaning subtraction. Squares meaning that your two terms in your binomial are perfect squared, so they're squared terms. When we factor those, that's going to give us the square root of the first, which is a, minus the square root of the second term, which is b, all times the square root of the first, which is a, plus the square root of the second, which is b. And looking at this expression, this may look familiar to you. Let's recall our multiplication of conjugate binomials. So if we have a minus b times a plus b, what do we get when we expand that out? Well, using FOIL, we're going to multiply our first terms of our binomial to give us an a squared. Then we're going to multiply the outsides. So that's a times b. It's going to give us ab. And then negative b times a, that's going to give us negative ba. But as we've said before, multiplying numbers, the order doesn't matter. So we could write that as a negative ab as well. And then a negative b times a b is going to give us a negative b squared. Collecting like terms, we see we have an a squared term. There's no other a squared term. We have an ab term, and there's another ab term here. And then we have a b squared term. There's no other b squared term. So we're going to collect those like terms to give us a squared. ab minus ab equals 0. So we're not going to write anything. Minus b squared. So expanding or multiplying conjugate binomials gives us a difference of squares. So to go in the reverse order, which is factoring, to factor a difference of squares, that's going to give us the product of two conjugate binomials. Let's look at an example. So one of the things about difference of squares factoring, as simple as it may appear, the first step is that you have to identify your expression as a difference of squares. So looking at our example, x squared minus 4, we analyze that the first term is a perfect square because we have an x squared. The second term is a perfect square because 2 times 2 is 4, making 4 a perfect square. And then they're being subtracted. So yes, this is a difference of squares. How do we factor this? Well, we can write this as x squared minus 2 squared. I wrote it as 2 squared just to show that it's the 2 that is squared, not the 4. Okay, so to factor this, we're going to write the square root of the first. So the square root of x squared is equal to x. And then the square root of 4, or as we wrote up there, the square root of 2 squared is just equal to 2, right? Remember, square rooting undoes the square, okay? So our factored form is going to be x minus 2, x plus 2. And I could have also written it as x plus 2, x minus 2. Again, we're multiplying these two binomials, so the order in which you show them does not matter. Pretty straightforward. Let's try some examples. Again, we can't just look at expressions and jump to difference of squares. We have to check to make sure that it is a difference of squares before we apply our formula. So let's look at question A. We have a 4x squared minus 9. Can we use our difference of squares formula? Well, we have a 4x squared. That is a perfect square. And we have a 9 that is also a perfect square. How can we rewrite this just to indicate something squared? And this step is not a mandatory step, but in teaching this, it's helpful to see what is being squared. So with 4x squared, what do we square in order to get 4x squared? Well, that's going to be 2x all squared, right? So it's a 2x that's being squared to give us our perfect square. Minus, for the 9, we're squaring a 3. So when we factor this, it's going to be the square root of the first, which is 2x, minus the square root of the second, which is 3, times the square root of the first, which is 2x, plus the square root of the second, which is 3. So again, we have a product of two conjugate binomials. And using our formula for difference of squares, we were able to factor this difference of squares. Let's try question 8. So is this a difference of squares? Well, to get 64x squared, we can take 8x and square it. Yep, so that's a difference, perfect square. And then 81, that's just 9 squared. So this is definitely a difference of squares. And I just want to write quickly that going back to our formula a squared minus b squared, the 8x would be considered our a, and the 9 would be considered our b, just for those who were not able to see the connection between our formulas. Okay, so what's the factored form? Well, we're going to take the square root of the first, which is just 8x, minus the square root of the second, all times the square root of the first, plus the square root of the second. Done. Easy. Let's try one more. So we have 36y squared minus 1. Is this a difference of squares? Let's check. I'm just going to move the screen over. So we have 36y squared. What do we have to multiply together or square to get 36y squared? That's going to be 6y all squared minus 1 squared. And for that 1, you don't even have to put the squared. We know that only 1 times 1 can give us 1. But when we factor this, square root of the first minus the square root of the second, all times the square root of the first plus the square root of the second. And easy breezy. Hardest thing about difference of squares factoring is being able to identify that it is in fact a difference of squares. Okay. So let's try some more difficult problems. A little bit more challenging. Remember when we were doing the other types of factoring problems? Make sure that the first factoring method that you look for is common factoring. If you common factor a greatest common factor out of an expression first before applying any other method, it makes the new expression that you have a little bit more simple or easier to factor, or it allows you to see a pattern or another method that you wouldn't have seen if you had not factored out that common factor. Okay, so just something to note. All right, so looking at this expression, is there a common factor first and foremost between 4x squared and 49y squared? 4, 49, nope, there's no number that can go into 4 and 49 other than 1. And then x squared and y squared, nope, nothing common there. So let's go to difference of squares factoring. Can we difference of squares factor this? Well, 4x squared can be rewritten as 2x squared. So it's the square of 2x minus 7y all squared. Okay. And again, this step is not a mandatory step, but it's helpful for some people when they're factoring using difference of squares factoring. So let's factor this. Square root of the first is 2x minus square root of the second, all times the square root of the first plus the square root of the second. Okay, so we didn't have to apply the common factoring piece here, but again, you should always check just to simplify your expression that you can factor. Let's try B. So first we have to look at our expression and identify whether or not it is a difference of squares polynomial expression. Looking at our coefficients, we have a 3 and a 27. Those two numbers are not perfect squares. And now looking at our variables, we have an x cubed and an x. Those are not squared. We have a cubed and we have just a lone x. So this is definitely not a difference of squares. Okay. Looking at the coefficients, we could have said they're not perfect squares and just stopped, not even having to analyze the variables. But sometimes you may get questions where the coefficients are perfect squares, but the variables are not perfect squares. So you need to pay attention to that as well. Both the variable and the coefficient have to be perfect squares in order for you to use this method. Okay, so it's not difference of squares right now, but what we said before is that we have to apply or look to apply our greatest common factoring method first. So can we find a common factor that we can factor out of our two terms? Looking at our coefficients, the highest number that can go into both a 3 and a 27 is a 3, so we can factor out the 3. And then looking at our variables, both of our terms have at least one x in common, so we can factor out an x, right? What's left in our first term? We divide out the 3, we divide out one of the x's, we're gonna be left with an x squared. And then in the second term, we divide out the 3x, that's gonna leave us with a -9 or -9. Okay. Are we finished? Well, when you are factoring, we want to make sure that we factor fully, which means that all of the factors that we get after our first factoring step should not be able to be factored again. If you can't factor your factors, then that means that your expression or your factored form is completely factored. So looking at the first term, 3x, we can't factor that again, but looking at the binomial inside of the brackets, we have an x squared minus 9. This is our difference of squares. So it is a factor that we got from the first factoring process, but we can factor that factor again. Okay, so we're factoring the x squared minus 9. So we're going to leave the 3x the way it is, but then we can break that down into square root of the first minus square root of the second times square root of the first plus the square root of the second. Okay, and again, notice how that 3x is still being multiplied to the new factored form of our original difference of squares expression. And we're done. Okay, so always check inside the bracket to see whether or not you can factor again. Awesome. So in this case, we were able to greatest common factor out first, and then after doing that step, we were able to see that we had a difference of squares in the bracket, which we could factor again. And the last one. So once again, this is not a difference of squares. We have a 2 and a 32, not perfect squares. We have an x cubed, we have an x in this expression, and then we have a y squared. So the y squared is a perfect square, but everything else in that term is not a squared value. So this is not a difference of squares, but we're going to check for our greatest common factor first. Looking at our coefficients, we can factor out a 2. And then our variables, we can factor out an x. And then what's left in each of our expressions is going to be an x squared minus 16. Factored out the x, so that's gone. Y squared. Okay, so that's our first factoring step. Now we have to check to see that our factors in this new expression can't be factored any further. 2x can't be factored any further. X squared minus 16y squared, that is a difference of squares. And when you're solving this, you don't have to write difference of squares or identify what's inside of the bracket. You're just going to simply go to the next step and factor again. So we have that 2x, which is going to remain 2x, but the x squared minus 16y squared can be factored again into the product of two conjugates. What are those two conjugate binomials? First one is going to be x minus 4y all times x plus 4y. And we're done. Okay. So that is difference of squares factoring. Pretty straightforward. Just make sure that you are identifying an expression as a difference of squares before you start using this method. And also, difference meaning subtraction. So do not get caught using this method when there is a plus sign in between your two square terms. That's something that catches a lot of students. They see the perfect square terms and they say, oh, yeah, difference of squares, but they fail to look at the plus in between. This cannot be used when you are adding two perfect squares.